Hello, math learners! Our lesson for today is about series and mathematical induction. The learning objectives are: you are going to differentiate series from a sequence. Use the sigma notation to represent a series. Find the sum of terms of arithmetic and geometric sequences. Prove formulas and equations using mathematical induction. And expand binomials using binomial theorem or Pascal's triangle. This is the Learning Pocket concept map. Under series and mathematical induction, we have formulas and equations, methods, binomial expansions, and applications. Let us recall sequences and series. A sequence is an arrangement of any objects or a set of numbers in a particular order, followed by some rule. If a sub 1, a sub 2, a sub 3, a sub 4, and so on denote the terms of a sequence, then 1, 2, 3, and 4 and so on denotes the position of the term. A sequence can be defined based on the number of terms, either finite sequence, where the number of terms is defined, or infinite sequence, where its terms are continuing indefinitely. Let us have the types of sequence. First, we have the arithmetic sequence. A sequence in which every term is created by adding or subtracting a definite number to the preceding number is an arithmetic sequence, like 2, 5, 8, 11, and so on. And the common difference is 3. A geometric sequence, a sequence in which every term is obtained by multiplying or dividing a definite number with the preceding number, is known as a geometric sequence, like 2, 4, 8, 16, 32. And the common ratio is 2. The third one is the harmonic sequence. A series of numbers is said to be in harmonic sequence if the reciprocals of all the elements of the sequence form an arithmetic sequence, like 1/2, 1/5, 1/8, 1/11, and so on. So 2, 5, 8, 11 is an example of an arithmetic sequence. The fourth one is Fibonacci numbers. Fibonacci numbers form an interesting sequence of numbers in which each element is obtained by adding two preceding elements, and the sequence starts with 0 and 1. Sequence is defined as f sub 0 is equal to 0 and f sub 1 is equal to 1, and f sub n is equal to f sub n minus 1 plus f sub n minus 2. For example, 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, and so on. So the first term is 0 followed by 1, and then you have 1. Add 1 and 1, you have 2. Add 1 and 2, you have 3. 2 and 3, you have 5, and so on. Let us have now the series and the partial sums. A partial sum is the sum of part of the sequence. Partial sums are sometimes called finite series. For example, the sequence of even numbers from 2 onwards. So we have the set of 2, 4, 6, 8, 10, 12, and so on. And the partial sum of the first four terms, which are 2, 4, 6, 8, of that sequence is equivalent to 20. So 20 is the partial sum. A series is the result when you add all the terms in a sequence. A series can be denoted by S sub n, where n refers to the number of terms. Thus, when it is an infinite sequence, produces an infinite series. For example, you have infinite sequence represented by a sub 1, a sub 2, a sub 3, a sub 4, and so on until a sub n. So for the infinite series, we have a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 plus a sub n, and so on. While finite sequence produces a finite series or partial sum, which is denoted by S sub n. So finite sequence, we have a sub 1, a sub 2, a sub 3, a sub 4, and so on until we have a sub n minus 2, a sub n minus 1, and we have the last term represented by a sub n. For finite series, we have a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 plus a sub n minus 2 plus a sub n minus 1 plus a sub n. By the way, this three dots here is called ellipses. Let us have an example. Find the indicated value for the series. We have 2 plus 4 plus 6 plus 8 plus 10 plus until the 10th term. So for the solutions, you have to look for a pattern to identify the other terms until the 10th term and express these terms as a sum. So it would be like this. 2 plus 4 plus 6 plus 8 plus 10 plus 12 plus 14 plus 16 plus 18 plus 20, which is equivalent to 110. The common difference is 2. So 2 plus 2 is 4, 4 plus 2 is 6, and so on. Again, the sum of the 10 terms is equivalent to 110. Next, find the indicated value for the series. The indicated is the sum of the 6 terms. So we have the first term, negative 1/4, plus the second term, negative 1/2, plus the third term, negative 1, plus negative 2, and so on. So for the solutions, you have to look for a pattern to identify the other terms until the 6th term and express these terms as a sum. So we have now negative 1/4 plus negative 1/2 plus negative 1 plus negative 2 plus negative 4 plus negative 8, which is equivalent to negative 63 over 4. So the sum of the 6 terms, we have negative 63 over 4. Let us have now the difference between sequences and series. For a sequence, it is a set of elements that follow a pattern. For the series, sum of elements of the sequence. For a sequence, the order of elements is important. For a series, order of elements is not so important. For finite sequence, we have an example 1, 2, 3, 4, 5. So no ellipses. For finite series, we have 1 plus 2 plus 3 plus 4 plus 5. So there is a last term, so no ellipses. For infinite sequence, we have an example 1, 2, 3, 4, and so on, represented by the ellipsis. And for infinite series, we have 1 plus 2 plus 3 plus 4 plus, and so on and so forth. Let us have the summation notation. This concept of getting the sum of terms can be expressed in a simpler manner using the summation notation, denoted by a Greek letter sigma. So this is the symbol for sigma. This can be used to indicate the sum of terms in a sequence. Partial sums are often written using the summation notation or sigma to mean add them all up. For example, we add up 1, 2, 3, and 4. So it would be like this. The summation of n from n equals 1 until 4. So you have to add 1 plus 2 plus 3 plus 4. And the summation or the sum or series is equal to 10. N will represent what to add. N is the initial number. You start at this value. And for here, you have to end up with this value or to go to this value. So there you started with 1 until 4. And take the sum, it's 10. Now this notation is read as the summation of n is n here from n is equal to 1 to n is equal to 4. The values of n begin from 1 to 4, which is 1, 2, 3, and 4. Start at the given value of n and end at the number above the sigma symbol. For example, write this summation, which is the summation of 2n from n is equal to 1 to n is equal to 5 in expanded form. Then find its value. For the solutions, all you have to do is to replace n consecutively with the integers from the value of the lower index to the value of the upper index and then simplify. So it would be like this. The pattern is 2n. So 2 times 1 plus 2 times 2 plus 2 times 3 plus 2 times 4 plus 2 times 5. So you have to end up until 5 only. And then simplify. 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6, 2 times 4 is 8, 2 times 5 is 10. Which will give you the sum of 30. So the summation of 2n from n is equal to 1 to n is equal to 5 is 30. Let us have another example. Write the summation of the square of n minus 1 from n is equal to 3 to n is equal to 5 in expanded form. Then find its value. So for the solutions, all you have to do again is to replace n consecutively with the integers from the value of the lower index. This is the lower index here, to the value of the upper index and then simplify. So the lower index is 3. You have to start with 3 and follow the pattern. The pattern is the square of n minus 1. So change n by 3. Then just copy minus 1 and then you square. You start with 3. Then followed by 4, minus 1, and then square, plus 5. You end up with 5, minus 1, then you square. Then simplify. 3 minus 1 is 2, you square it 4. 4 minus 1 is 3, square it 9. 5 minus 1 is 4, square it 16. Which will give you a total of 29. So the summation of the square of n minus 1 from n equals 3 to n equals 5 is 29. Let us have the common types of series: the arithmetic series and the geometric series. So we will just concentrate with these two. For arithmetic series, an arithmetic series is the sum of the terms of the arithmetic sequence. If the arithmetic sequence is 2, 5, 8, 11, 14, then the arithmetic series is 2 plus 5 plus 8 plus 11 plus 14. For the arithmetic series, the formula for finding the sum of an arithmetic sequence, we have the sum denoted by S sub n of the first n terms of an arithmetic series is, first, we have S sub n is equal to n over 2 times a sub 1 plus a sub n. If the given is the first term and the last term. Or you can have S sub n is equal to n over 2 times the quantity 2 times a sub 1 plus the quantity n minus 1 times d. Or you can have this form where a sub 1 is the first term, a sub n is the nth term, n is the number of terms, and d is the common difference. The first formula is used when the first term and the nth term, or simply the last term, and the number of terms are known. The second formula is used when the first term, the number of terms, and the common difference are known. Let us have an example. Find the sum of 10 terms if the first term is 5 and the 10th term is 68. For the solutions, we have to identify first the value of n, which is 10, a sub 1 is 5, a sub 10 is 68. So since the first term is given and the last term is also given, we are going to use the first formula. And then substitute 5 to a sub 1 and 68 to a sub n. And then simplify. So we have 10 over 2 times 68 plus 5 is 73. And the sum of the 10 terms is 365. Let us have the second example. Find the sum of the 10 terms if the first term is 5 and the common difference is negative 7. For the solutions, let us identify first the value of n, which is 10. First term is 5, the common difference is negative 7. And then, using the second formula, all you have to do is to substitute 10 to n here, and 5 to a sub 1, 10 to n, and the common difference is negative 7. And then simplify. So 2 times 5 is 10, 10 minus 1 is 9 times negative 7. And 9 times negative 7 is negative 63 plus 10 is negative 53 times 5. So the sum of the 10 terms is negative 265. Next, let us have geometric series. A geometric series is the sum of the terms of a geometric sequence. If the geometric sequence is 2, 4, 8, 16, 32, then the geometric series is 2 plus 4 plus 8 plus 16 plus 32. And the formula for finding the sum of a geometric sequence, we have the sum represented by S sub n of the first n terms of the geometric series is defined as, for finite geometric series, we have S sub n is equal to a sub 1 minus r times a sub n all over 1 minus r. And the other one, S sub n is equal to a sub 1 times 1 minus r raised to n all over 1 minus r, where r should not be equal to 1. And also with the first formula. For infinite geometric series, we have S is equal to a sub 1 over 1 minus r. In infinite geometric series, if the absolute value of r is less than 1, the infinite series has a sum. And if the absolute value of r is greater than or equal to 1, the series does not have a sum. where a sub 1 is the first term, a sub n is the nth term, n is the number of terms, and r is the common ratio. Let us have an example. Find the geometric series given 4 plus 1 plus 2 plus until the fifth term. For the solutions, the first term is 4. The common ratio is 1/2 and n is equal to 5. To find the ratio, all you have to do is to divide the second term with the first term or the third term with the second term. So using the formula, a sub n is equal to a sub 1 times 1 minus r raised to n all over 1 minus r. All you have to do is to substitute the values. A sub 1 is 4, so it's here. 1 minus the ratio is 1/2 raised to 5 because there are 5 terms. And 1 minus 1/2. Then simplify 1 minus 1 over 32 times 4 all over 1 minus 1/2. So you have 31 over 2 times 4 over 1/2. Just take the reciprocal of 1/2 and multiply it to 31 over 8. Just reduce 4 with 32. So we have 31 over 8. And then the sum of the 5 terms is equivalent to 31 over 4. You can reduce 8 with 2. So 31 over 4. Let us have another solutions. Using the other formula, which is S sub n is equal to a sub 1 minus r times a sub n over 1 minus r. First term again is 4. The ratio is 1/2. N is 5. N is 5. And the fifth term is 1/2. You can multiply the third term here by 1/2. And whatever the result, multiply it by 1/2 in order to get the fifth term, which is 1/4. So all you have to do is to substitute. First term is 4, ratio is 1/2. The nth term or the last term is 1/4 over 1 minus 1/2. And then let's simplify. 1/2 times 1/4 is 1/8. And then 4 minus 1/8, that is 31 over 8. 1 minus 1/2 is 1/2. Simplify further, so we have 31 over 8 times 2 over 1, which is still equivalent to 31 over 4. Again, to find r, you can use the second term, divide it with the first term, which will give you 1/2. Or the third term, divide it with the second term, the result is still 1/2. To check, we have r is equal to 1/2, a sub 4 is also 1/2, a sub 5 is 1/4. So just add 4 plus 2 plus 1 plus 1/2 plus 1/4. It will give you 31 over 4. Let us have another example. Find the geometric series given 5 plus 1 plus 1/5 and so on. For the solutions, a sub 1 is 5. The common ratio is 1/5. You can have second term divided with 5, which is 1/5. Or 1/5 divided by 1, which is also 1/5. We will be using the formula for infinite geometric series because the indicator is the ellipsis. So the formula is S is equal to a sub 1 over 1 minus r. So a sub 1 is 5 over 1 minus 1/5. Simplify 5 over 4/5. So just take the reciprocal of 4/5, that's equivalent to 5/4. That is 25 over 4. So the sum of the geometric series wherein the first term is 5 and the ratio is 1/5 is 25 over 4. Let us have now the mathematical induction. Mathematical induction is a principle for proving certain mathematical theorems, proposition, or formula. It is a technique used to establish a given mathematical statement for all natural numbers. This principle is analogous to the principle of domino effect. That is, dominoes are aligned and erected so that when the first one falls, the next domino will follow to fall, and so on. Mathematical induction allows us to prove that a statement is true in 3 steps. The first is the base case. We have to prove that the statement is true for n is equal to 1. Number 2, the inductive hypothesis. We have to assume that the statement is true for n is equal to k. And the third one is the inductive step. We have to use the inductive hypothesis to show that the statement is true for n is equal to k plus 1. For example, let us have the proof of the sum of the first n integers with the formula n times the quantity 1 plus n over 2. This is the formula of Gauss in identifying the sum of the first n integers. For the first step, the base case, we have to show that it is true for n is equal to 1. So if n is equal to 1, the entire sequence is just 1, and therefore the sum is 1. So using this equation, n times the quantity 1 plus n over 2, all you have to do is to replace n by 1. So 1 times the quantity 1 plus 1. Then simplify. This is 1 plus 1 is 2 times 1 is 2 over 2, and 2 over 2 is 1. So this equation is equal to 1, which is true. For step 2, we have to assume that it is true for n is equal to k. So assume that the sum of the first k positive integers is k times the quantity k plus 1 over 2. So for n times 1 plus n over 2, or can be written as n times the quantity n plus 1 over 2, all you have to do is to change n by k. So we have now k times k plus 1 over 2. In other words, assume that 1 plus 2 plus 3 plus and so on until k is just simply equivalent to k times the quantity k plus 1 over 2. This series is the representation of the sum of the first n integers. And we have to assume that this is true. For the third step, we have to let n is equal to k plus 1. And then prove that 1 plus 2 plus 3 plus k plus 1, which is equivalent to the quantity k plus 1 times the quantity k plus 1 over 2 is also true. We must show that the sum of the first k plus 1 positive integers is k plus 1 times the quantity of k plus 1 over 2. So it would be like this. From the first step, we have n times 1 plus n over 2. Second step, we have k times the quantity k plus 1 over 2. Until we reach the third step, so we add 1 to k, so that's k plus 1. And then we add 1 to k plus 1, so we have k plus 1 over 2. For the solutions, so for 1 plus 2 plus 3 plus k, then adding k plus 1, this expression is equivalent to k times 1 plus k over 2. And copy k plus 1. And copy this part. Then we have to simplify this portion here. So the LCD is 2. 2 divided by 2 is 1 times k times the quantity 1 plus k, or k plus 1. So it's here. 2 divided by 1 is equal to 2 times k plus 1. So it's here. And then you multiply, distribute k to k plus 1. So we have k squared plus k plus distribute 2 to k plus 1. So 2k plus 2 over 2. And then k plus 2k is 3k. So we have k squared plus 3k plus 2 over 2. And then we have to factor k squared plus 3k plus 2. So one of the factors is k plus 2. So k plus 2, and the other factor is k plus 1 over 2. Now the k plus 2 can be equated into k plus 1 plus 1. So just separate 2 into 1 and 1. Wherein k plus 2 is equal now to k plus 1 plus 1, in which it is now similar to this portion here at the right side. So you can enclose this in a bracket. So what we have, the left side of the equation is equivalent to the right side of the equation. And the third step now is true. Let us have example number 2. Prove that the sum of the first n positive odd integers is n squared. So the first n positive odd integers can be written as 1 plus 3 plus 5 and so on until you will have this formula 2n minus 1 to get the next term, which is equivalent to n squared. So the proof, for step 1, we have to show that it is true for n is equal to 1. For the solutions, we have to write 1 plus 3 plus n plus and so on until 2n minus 1 is equal to n squared. So for n is equal to 1, just take one term. 1 is equal to 1 squared. This portion here. So change n into 1. And 1 squared is equivalent to 1. So 1 is equal to 1 is true. Take note, for the statement to be true, it must be true for n is equal to 2, 3, 4, and so on. So let us check. For n is equal to 2, so we have to use the first two terms now. 1 plus 3 is equal to, change n into 2, it's 2 squared. 1 plus 3 is equal to 4. So 4 is equal to 4. It is also true for n is equal to 2. Let us try. For n is equal to 3. So we will be using now the first three terms. 1 plus 3 plus 5 is equal to 3 squared, because by this time n is equal to 3. 3 squared is 9. And 1 plus 3 plus 5 is also equal to 9. Meaning, this is also true for n is equal to, let us try for n is equal to 4. So, next to 5 we have 7. So 1 plus 3 plus 5 plus 7. So by this time our n is 4. So it's 4 squared, which is 16. And 1 plus 3 plus 5 plus 7 is equal to 16. Therefore, 16 is equal to 16. It's also true. And so on and so forth. For step 2, we have to assume that it is true for n is equal to k. So we have 1 plus 3 plus 5 plus 2n minus 1 is equal to n squared. And we will change n into k. So this is now the new equation. 1 plus 3 plus 5 plus and so on 2k, change n to k minus 1, and n squared becomes k squared. And this is true because it is an assumption. So when it is an assumption, you have to treat it as a fact for the rest of this example. For step 3, we have to prove that 1 plus 3 plus 5 and so on until 2k minus 1 plus 2k plus 1 is equal to the square of k plus 1 is true for n is equal to k plus 1. So this expression equivalent to k squared. That is under step 2. By this time, we have to add k plus 1. From here, we have to have now 1 plus 3 plus 5 plus the quantity 2k minus 1 plus 2k plus 1 is equal to the square of k plus 1. For the solutions, it would be like this. 1 plus 3 plus 5 plus 2k minus 1 until here, and then you add 2, change k into k plus 1, and there is a negative 1, so it's negative 1 here, which is equivalent to k squared. And then since you're adding this expression, you also add it to the other side. And then all you have to do is to simplify. Distribute 2 to k plus 1, so you have 2k plus 2 minus 1. And also with this one, you have to distribute. So what we have now is, in this part, you have 2k minus 1, just copy. 2 minus 1 is 1. So we have now 2k plus 1. That is why here, we added 2k plus 1. It's here. This is also equivalent to 2k plus 1. Now, remove the parentheses here. So we will have now k squared plus 2k plus 1. And this is factorable. So all you have to do is to factor. The factors are k plus 1 and k plus 1. And express this as a square of binomial because the two binomial factors are the same. So this is equivalent to the square of k plus 1. So meaning, this equation is true for n is equal to k plus 1. Example number 3, we have to prove the sum of the consecutive cubes. So we have now 1 cube plus 2 cube plus 3 cube plus until n cube, which is equivalent to n cube times the square of n plus 1 over 4. The proof we have for step 1, we have to show that it is true for n is equal to 1. So for the solutions, using the n is equal to 1, so you just use the first term. So 1 cube is equal to n squared times the square of n plus 1 over 4. So all you have to do is to change n into 1. So we have now 1 squared times the quantity 1 plus 1. And then you square, then all over 4. So we have 1 plus 1 is 2, square it, it's 4. Then we have 1 times 4 over 4. So it's equivalent to 1. And this is true. And let us check using n is equal to 2. So by this time, we have to use the first two terms. 1 cube plus 2 cube now. And change n into 2. So 2 squared times the quantity 2 plus 1 squared, all over 4. So this is 3. Then you square 3, it's 9 times 4 divided by 4 is 9. Because 9 times 4 is 36 divided by 4, it's 9. And 1 cube is 1, 2 cube is 8. 1 plus 8 is 9. So this is true. Let us check using n is equal to 3. So by this time, we have to use the first three terms. 1 cube plus 2 cube plus 3 cube. So change n into 3. So 3 squared now times the quantity 3 plus 1 and then you square. All over 4. So 3 squared is 9. 3 plus 1 is 4. Then square over 4. So 9 times 16 over 4. So we have 36 is equal to 36. You can divide 16 by 4, which is equivalent to 4, and then multiply it with 9, it's 36. So 36 is equal to 36, which is true. And so on and so forth. For step 2, we have to assume that it is true for n is equal to k. So just change n into k. And k squared times the square of k plus 1 over 4 is true. This is an assumption. And expressing this in 1 cube plus 2 cube plus 3 cube and so on until k cube, which is equivalent to k squared times the square of k plus 1 over 4. For step 3, you have to prove that this expression here is equivalent to the square of k plus 1 times the square of k plus 2 all over 4. And it should be true for n is equal to k plus 1. So for the solutions, you have to add the cube of k plus 1. So the last here is k cube. Just add cube of k plus 1. Add it also to the other side. And then simplify this part. The LCD is 4. So what we have is k squared times the square of k plus 1 plus 4 times the cube of k plus 1. And then you can factor out the square of k plus 1. So here. So what we have is k squared times square of k plus 1 divided by the square of k plus 1 is k squared plus 4 times the cube of k plus 1 divided by the square of k plus 1 is equal to k plus 1, then over 4. And then you multiply 4 by k plus 1, so you have 4k plus 4. And then factor the trinomial. The factors are k plus 2 and k plus 2, wherein you can change this into the square of binomial. So what we have now is the square of k plus 1 times the square of k plus 2 over 4. Therefore, this expression is equivalent to this, and this is true for n is equal to k plus 1. Next, let us have the binomial theorem. The binomial theorem or binomial expansion describes the algebraic expansion of powers of a binomial. According to the theorem, it is possible to expand the polynomial of the quantity x plus y raised to n into a sum involving terms of the form ax raised to b, y raised to c, where the exponents b and c are non-negative integers, with b plus c is equal to n, and the coefficient a of each term is a specific positive integer depending on n and b. For example, for n is equal to 4. So we have x plus y raised to 4. So we have the quantity x plus y raised to 4. And the expansion is x to the exponent of 4 plus 4x cubed y plus 6x squared y squared plus 4x y cubed plus y raised to 4. According to the theorem, it is possible to expand any non-negative power of x plus y into a sum of the form the quantity x plus y raised to n into n choose 0 x raised to n y raised to 0 plus n choose 1 x raised to n minus 1 y raised to 1 plus n choose 2 x raised to n minus 2 y squared, and so on and so forth. Using the summation notation, it can be written as the quantity x plus y raised to n equals to the summation of n choose k x raised to n minus k y raised to k from k is equal to 0 to n, which is equivalent to the summation of n choose k x raised to k, y raised to n minus k, where n choose k is equal to n combination k is equal to n factorial over the quantity of n minus k factorial times k factorial. This is the formula of combination when we had our discussion on permutation and combination. For example, 3 choose 2 is equal to 3 combination 2, which is equivalent to 3. And using your calculator, you have this NCR for the combination. All you have to do is to press Shift 3 and this division key, wherein the upper part is the combination or the NCR, then press 2 and then equals, and it will give you 3. For example, illustrating the binomial expansion, the cube of x plus y is just simply equivalent to the quantity of x plus y times the quantity of x plus y times the quantity x plus y. And it will give you like this, which will give us x cubed plus 3x squared y plus 3xy squared plus y cubed. You can use the special products or simply just multiply the three binomials in order to get the expansion. Using the binomial theorem, we have the cube of x plus y equals 3 choose 0, which is equivalent to 1. Then copy x cubed. 3 choose 1, which is 3. Then x squared y. 3 choose 2 is 3. xy squared. Then 3 choose 3 is 1. That's y cubed. And then just simplify further. So the cube of x plus y is equal to x cubed plus 3x squared y plus 3xy squared plus y cubed. Just remember, if the exponent is 3, there are 4 terms in the expansion. 1, 2, 3, 4. And the exponent of the first term is decreasing. So the first term is x, so you start with 3, followed by 2, followed by 1. After that is 0. There's no need to write x raised to 0 because that is simply equivalent to 1. And the exponent of the second term, which is y, is increasing. So for the first term, you have y is equal to 0. So again, there's no need to write y is equal to 0 because that is equivalent to 1. Then you start here y with exponent 1, then y squared, then y cubed. Next, given the cube of x plus 2, so following the same rule, the second term now is 2 instead of y, and then just simplify it. So 2 times 3 is 6. 2 times 2 is 4, times 3 is 12. Then 2 cubed is 8. Still, there are 4 terms in the expansion because the exponent is 3. So 1, 2, 3, 4. Using the binomial theorem, we have 3 choose 0, it's equivalent to 1. 3 choose 1 is 3. 3 choose 2, it's 3. 3 choose 3 is 1. Still, you will get the same answer. And when you're given the cube of the difference of x and 2, the terms of the answers are the same. They differ only with the signs. The signs are alternating. So the first term is with positive, then followed by a negative, then positive, then negative. And using the binomial theorem, it will give you the same answer. Again, they differ only with the signs. Positive, negative, positive, negative. Because the cube of negative 2 is simply negative 8. Binomial expansion can be done also using the Pascal triangle. Pascal's triangle is a triangular array of the binomial coefficients that arises in probability theory, combinatorics, and algebra. It is named after the French mathematician Blaise Pascal. So this is how the Pascal triangle looks like. You have 1, then 1 here and 1 here, then 1 plus 1 is 2, 1, then 1 plus 2 is 3, 2 plus 1 is 3, so 1 in all sides, and so on and so forth. For the expansion, so you start with a 0 exponent, so the binomial with 0 exponent, the binomial x plus y with 0 exponent, it is equivalent to 1. So it's here, it's 1. And then, when you raise the binomial into exponent 1, so the result is x plus y. So the numerical coefficients of x is 1. So it's here 1. And the numerical coefficient of y is 1. It's also here. When you raise it to 2, you have the square of x plus y. The result is x squared plus 2xy plus y squared. The numerical coefficient of x squared is 1. So it's here. And 2 here. 1 here, it's here. And so on and so forth. Using the Pascal triangle, what is the value of 5? Choose 2. So using the Pascal triangle, this is row 0, row 1, row 2 until row 5. This first one is the 0th element, first element, and the second element. So this will mean you have the 5th row and then choose the second element. And this is equivalent to 10. So 5 choose 2. Here, this part is simply equivalent to 10. So again, you have to look for the second element in the 5th row of the Pascal triangle, and the value of that element will be 10. And using your calculator, 5 choose 2 or 5 combination 2 is equivalent to 10. Another example, expand the quantity x plus y raised to 4 using Pascal triangle. So using the Pascal triangle, you have this part. Exponent is 4. You add 1 and 3. So it's 4. 3 plus 3, 6. 3 plus 1 is 4. So since the exponent is 4, there are 5 terms. Let us try to find out. 1, 2, 3, 4, 5. 5 numerical coefficients for the 5 terms. So all you have to do is to write the first term with exponent 4. Then second term here, exponent 3, and going down 2, 1, 0. And then for the second term, you can reflect the second term on the second term of the expansion. Y, then the exponent will increase. You have now y squared, y cubed, y exponent 4. Let's count 1, 2, 3, 4, 5. So there are 5 terms. Just simplify. So the expansion is x raised to 4 plus 4x cubed y plus 6x squared y squared plus 4x y cubed plus y exponent 4. Well, let us have another example. Expand the quantity x plus 2y raised to 4 using Pascal triangle. So again, in Pascal triangle, the coefficients, we have 1, 4, 6, 4, 1. And there are 5 terms. So this is 1, 2, 3, 4, 5. So for x, the degree or the exponent is decreasing. So 4, 3, 2, 1, 0. And then for the second term, you have there 2y. So 0, 1, 2, 3, 4. Then just simplify. This is equivalent to 1. So that is why you need not reflect this. Then this is equivalent to 2 times 4, it's 8. 2 squared is 4 times 4, it's 24. 2 cubed is 8 times 4 is 32. And x exponent 0 is 1. 2 to the exponent of 4 is 16. Times 1, it will give you 16 later on. So the final answer is x to the exponent of 4 plus 8x cubed y plus 24x squared y plus 32xy plus 16y raised to exponent 4. And when you are given the quantity x minus 2y raised to 4, so all you have to do is you will have the same answer, but the signs are alternating. So positive, negative, positive, negative, positive. Let us have now the applications of series. First one is an application of arithmetic series. The problem is, a construction company will be penalized each day of delay in construction for breach. The penalty will be 4,000 for the first day and will increase by 1,000 for each following day. Based on its budget, the company can afford to pay a maximum of 165,000 toward penalty. Find the maximum number of days by which the completion of work can be delayed. For the solutions, let n be the number of days delayed. Let us form the sequence. We have 4,000 as the first penalty. Then it will increase by 1,000. So 4,000 plus 1,000 is 5,000. Then plus another 1,000, 6,000, and so on. Then the series form will be 4,000 plus 5,000 plus 6,000 and so on. And the total or the sum is 165,000. So this is our S sub n. First term is 4,000. The common difference is 1,000. So using the formula of the arithmetic series, we have to substitute 4,000 to the first term and 1,000 to D. S sub n is 165,000. And we will be solving for n, the number of days delayed. Then 2 times 4,000 is 8,000. Then distribute 1,000 to n minus 1. So 1,000 n minus 1,000. So we have now 8,000 minus 1,000 is 7,000 plus 1,000 n is equal to 165,000. And then we can simplify. We can remove the denominator 2 by multiplying both members of the equation by 2. So what we have, 2 divided by 2 is 1. So n times 7,000 is 7,000 n. N times 1,000 n is 1,000 n squared. And 2 times 165,000 is 330,000. And then you have to simplify, divide each by 1,000. So what is left is 7n plus n squared equals 330. And transpose 330, so you have negative 330 is equal to 0. You can factor n squared plus 7n minus 330 into n minus 15 times n plus 22. Equate to 0. And then solve for n, equate each factor to 0. So n minus 15 equals 0 and n plus 22 equals to 0. So n is equal to 15 and the other is n is equal to negative 22. Since n will represent the number of days delayed, we are going to use n is equal to 15. Therefore, the answer is there are 15 days by which the completion of work can be delayed. For example number 2, this is an example of a geometric series. A certain community decided to celebrate Christmas as a Thanksgiving by donating 1 peso on December 1, 2 pesos on December 2, 4 pesos on December 3, and so on through December 25 to a charity. The donations form a geometric series. What is the total amount of donation? Let us have the solutions. The geometric sequence form is 1, 2, 4, and so on. For the geometric series, 1 plus 2 plus 4. So, n is equal to 25 because it's until December 25. The first term is 1. The common ratio is 2. To find the ratio, you can divide 2 by 1, which is 2, or 4 by 2, which is still 2. So we can use the formula a sub n is equal to a sub 1 times the quantity 1 minus r raised to n all over 1 minus r. So all you have to do is to substitute the given to the formula. A sub 1 is 1, then 1 is constant minus 2, that's the ratio, raised to 25, that's the value of n, 1 minus r, which is 2. And then it is equivalent to negative 33,554,431 over negative 1. And then simplify, it will give you 33,554,431. So the total amount of donation is 33,554,431 pesos. Do you have questions? If there is none, see you next time. Bye!